Pick up a small fridge magnet and hold it above a paperclip resting on a table. The paperclip jumps. You will not be surprised. You have seen this happen 100 times. But think about what just occurred. The entire gravitational pull of the planet beneath you, a ball of rock and molten iron 6,000 kilometers deep, was just defeated by a sliver of magnetized metal you can fit in your palm. This is not a quirk. It is the surface signal of an unsolved problem 10 to the 38th deep, and it is the reason that, in 2008, a federal lawsuit in Hawaii tried to stop the largest scientific experiment ever built. The plaintiffs believed the Large Hadron Collider might create a black hole that would consume the Earth. What they did not realize was that the question underneath their fear was older, stranger, and more open than even the physicists they were suing had managed to answer. So what was actually being built underneath the border between Switzerland and France, and what was the universe really being asked? Settle in, subscribe if you haven't already, and stick around, because the answer involves a magnet, a tunnel, and a question. Physics has been inside for 30 years. Let's begin. Part 1. A Courthouse in Honolulu. On the 21st of March 2008, a man walked into a federal courthouse on the island of Oahu carrying a stack of papers. The man was named Walter Wagner. He was not famous. He was not a physicist of any standing the community would have recognized. He had once been a radiation safety officer at a research facility in California, and he had spent a fair part of his life convinced that one of the most ambitious experiments in human history was about to end the world. On that morning in Honolulu, he was no longer just a worried man. He was a plaintiff. His co-plaintiff, a Spanish writer named Luis Sancho, joined him on the filing. Together they walked into the United States District Court for the District of Hawaii and submitted a civil complaint that, on its face, sounded like the opening of a science fiction novel rather than the start of a real legal proceeding. The defendants on that complaint were not minor. The first name listed was the European Organization for Nuclear Research, the institution most people simply call CERN. The second was the United States Department of Energy. The third was the National Science Foundation. The fourth was Fermilab. Four of the most serious, most well-funded, most decorated research institutions in the world, named together in a single civil suit, accused of preparing to do something they could not undo. The relief Wagner and Sancho were seeking was extraordinary. They wanted a federal judge sitting in a courtroom thousands of kilometers from the Swiss-French border to order the largest scientific experiment ever built to stop before it had a chance to begin, to stop specifically before the Large Hadron Collider could attempt its first high-energy collisions, which at the time were only weeks away. To understand why two men were standing in front of a federal judge in Hawaii asking for an injunction against an underground physics experiment in Switzerland, you have to understand what they thought might happen. Wagner and Sancho believed that when the Large Hadron Collider began smashing protons into each other at energies humans had never produced before, it might accidentally create a black hole. They did not mean a small, harmless one. They did not mean a glowing dot of theoretical interest that would vanish before it did anything at all. They meant a real, persistent gravitational object, something that would slip out of the apparatus, sink down through the Swiss bedrock under its own gravity, and continue sinking. They meant something that would accrete matter as it fell, growing as it went until it reached the center of the Earth, and that once it reached the center, would keep eating. They imagined a process that, once started, could not be stopped. The end of the planet, in their fear, would not come as fire or as flood. It would come as silence, as the slow consumption of the world from the inside. That was not the only thing they feared. They had a second hypothesis ready, in case the first one did not turn out to be the danger. They were afraid of an object called a strangelet. A strangelet, in some theoretical models, is a small fragment of so-called strange quark matter, a kind of matter made not just of the ordinary up and down quarks that build the protons and neutrons inside every atom, but also of strange quarks, in roughly equal proportion. In the worst imagined scenarios, such a fragment, if it ever existed, might be more stable than ordinary nuclear matter. It might, when it touched ordinary atoms, persuade them to rearrange themselves into more strange matter. A chain reaction, in the imagination of the most cautious thinkers, that would convert the Earth into a single dense, dark sphere of something that was no longer Earth at all. Wagner and Sancho, on that March morning, were asking a federal judge to take both of these possibilities seriously enough to keep the collider switched off. It would be easy, looking at the filing now, to write the whole thing off as a courtroom curiosity. A pair of worried citizens, a sympathetic clerk, a federal judge who would inevitably find some procedural reason to dismiss the case. And that is more or less what happened. The lawsuit was eventually thrown out, on the grounds that no United States court had jurisdiction over a particle accelerator operated by an international consortium underneath a border in Central Europe. But the dismissal did not address the physics. The physics had to be addressed somewhere else, by other people in other places, and it was. The question Wagner and Sancho were asking, stripped of the lawsuit's hysteria and its strange theology and its insistence on 50-50 odds, had been written about in peer-reviewed physics journals for nearly a decade before they walked into that Honolulu courthouse. The answers had been worked out, the objections had been raised, the objections had been answered, and then the answers had been written up by CERN's own independent safety assessment group and signed by some of the most respected names in the field. A few months after the lawsuit was filed, Walter Wagner appeared on a television program called The Daily Show. The host that night was John Oliver. The interview has become a kind of small classic of how science and public anxiety meet on a television set. Oliver asked Wagner what he thought the actual odds were that the Large Hadron Collider would destroy the Earth. Wagner answered, in the most plain way you can imagine, that the odds were 50-50. Oliver tried, with that careful tone interviewers use when they want to make sure they have heard correctly, to ask the question again. Wagner explained himself. The odds were 50-50. It would either happen or it would not. He was treating probability as a binary thing. The world would end or it would not, so the chance of either outcome was the same as the chance of a coin flip. Oliver, to his credit, did not laugh on screen. He simply, quietly, kept asking the question, and Wagner kept answering it the same way. It is one of the most accidentally illuminating exchanges in the history of public conversation about probability, and it is also, in retrospect, the thing most people remember about the lawsuit. Not the legal filing, not the defendants, not the physics, the 50-50. But the question underneath the interview, the question underneath the lawsuit, the question underneath the bemused commentary that filled the next several months of science journalism was not a frivolous one. Serious physicists had written serious papers exploring the possibility that the Large Hadron Collider, under a specific set of theoretical assumptions, might in fact produce microscopic black holes. The papers had been published in respected journals, the numbers had been worked out in detail, the predicted rate of black hole production, under the assumptions in question, had been calculated. The signatures the collider's detectors would see if such an object formed had been spelled out. The question of whether those objects, if produced, would be dangerous had been considered. The question of how those objects would actually behave, given the laws of quantum mechanics and general relativity working together, had been computed. The reason CERN commissioned its own independent safety assessment was not because it was worried about the lawsuit. The lawsuit on its own was a procedural nuisance. The reason was that the theoretical possibility was real enough on paper that the institution responsible for running the most ambitious experiment ever built decided it would be irresponsible not to answer the question publicly, formally, and with the most respected physicists they could assemble. The Safety Assessment Group's report was published in 2008. It is a strange document if you have never read one. It treats the lawsuit's claim with complete seriousness. It does not dismiss the question as foolish. It walks through the physics step by step. It explains what would have to be true for the lawsuit sphere to be justified. It explains why each of those things is not true. And it does so in language that is calm enough that, if you read it now, you might find it almost meditative. So the story really begins not in Honolulu, but in the gap between what the lawsuit thought it was asking and what physics had already decided was the actual question. The lawsuit thought it was asking whether a machine might destroy the world. Physics had already understood that the underlying question was something stranger. Could a machine on Earth, even in principle, even under the most generous theoretical assumptions, produce something we would recognize as a black hole? And if it could, what would happen to that black hole between the moment of its creation and the moment, however many billionths of a second later, that the detectors recorded what was left of it? The lawsuit's monster, if it could exist at all, had a lifetime to live, and that lifetime was the thing the physics had to settle. The lawsuit's filing date matters in a way that it would not matter for an ordinary courtroom drama. The Large Hadron Collider had been under construction for nearly 2 decades. The decision to build it had been made in the late 1980s. The tunnel had been excavated, the magnets had been built, the cryogenic systems had been installed, the detectors had been assembled piece by piece in vast underground caverns. The cost had been measured in billions of euros. The collaboration had brought together physicists from more than 30 countries, and it was all coming to a head. The first beams were expected within months, the first high-energy collisions within months after that. When Wagner and Sancho walked into the Honolulu courthouse, they were not stopping an idea. They were trying to stop an actual machine that was already, in a real and physical sense, almost finished. There were people inside the tunnel, in the spring of 2008, doing final checks on the magnets. There were people in the control room walking through the first commissioning runs. There were physicists who had spent their entire adult lives waiting for the moment when the collider would finally turn on. The lawsuit was, among other things, a profound failure of timing. It arrived at the very last possible moment. It is worth slowing down here, because the temptation in a story like this is to skip past the courtroom drama and get to the physics. The physics is, in many ways, the more interesting part. But the courtroom drama matters. It matters because the lawsuit was, in its own clumsy way, an articulation of something a great many people felt, even if most of them never put it into a legal filing. The Large Hadron Collider was, and is, a thing of almost incomprehensible scale and ambition. It is the kind of project that, when you describe its specifications honestly, sounds like a science fiction premise. A 27-kilometer ring buried 100 meters underground. Beams of subatomic particles accelerated to within 3 meters per second of the speed of light. Magnets cooled to within 2 degrees of absolute zero. Energies, at the collision point, that had not existed since the first microseconds after the Big Bang. It would be strange, in some ways, if nobody had filed a lawsuit. The wonder is not that someone tried to stop it. The wonder is that almost everyone else in the end decided to let it happen. The judge in Honolulu dismissed the case in late 2008, on the grounds that the United States District Courts did not have the authority to enjoin a particle accelerator operated by an international consortium under a border in Central Europe. The appeals process worked its way through the system over the following years. The case was, in legal terms, finished by 2010. The Large Hadron Collider, in the meantime, had begun its first physics runs. It had recorded collisions. It had produced data. It had not produced any black holes that ate the Earth, because, as we are about to see in detail, it could not have done so under almost any reasonable set of assumptions. But the question Wagner and Sancho had asked in their clumsy way, in front of a federal judge on Oahu, had echoes that did not stop when the case was dismissed. They echo in a sense into the present. They echo because the answer the universe has given to that question is more interesting than the question itself. To get to that answer, we have to understand the machine. We have to understand what it was that was switching on, under the border between Switzerland and France, on the day that Wagner and Sancho filed their suit. We have to understand what the world looked like, in the most literal physical sense, 100 meters under the surface of the Earth, where the most ambitious experiment ever conceived was about to start asking questions of reality at energies nature had not produced in our part of the cosmos for 13.8 billion years. Because the question Wagner and Sancho were really asking, even if they did not phrase it this way, was a question about scale, about energy, about what happens when you take something almost unimaginably small and pour into it an amount of energy almost unimaginably concentrated. The answer involves a tunnel, and a beam, and a temperature lower than deep space, and a speed barely distinguishable from the speed of light. It involves protons that go around a 27-kilometer ring 3,000 times in the duration of a single human blink. It involves 4 detectors the size of cathedrals, buried in their own caverns, watching what comes out of the collisions and trying to write it down before the next collision happens 25 billionths of a second later. The lawsuit, in a way, was the price the world paid for, not understanding what was already being built underneath it. The next part of the story is what was being built. Part 2. The machine. The lawsuit was trying to stop. Beneath the border between Switzerland and France, roughly 100 meters down, there is a tunnel. It is not a small tunnel. It is not the kind of tunnel you walk through casually. It is a ring, almost perfectly circular, with a circumference of 26.659 kilometers. Inside that ring, packed into a tube narrower than a human arm, runs a machine that, when it is operating, is among the most extreme environments humans have ever assembled in one place. The tunnel itself is older than the current experiment. It was originally dug in the 1980s for a different collider, the Large Electron-Positron Collider, which finished its scientific life in 2000. When that machine was decommissioned, the tunnel did not go away. It was already there, in the rock under the cantons of Geneva and the French Department of Ain, and the international consortium of physicists who had finished one experiment in it decided that they would not waste the next chapter. They began, even before the Large Electron-Positron machine had finished its final runs, designing a new experiment that would take its place inside the same circle. The new experiment was called the Large Hadron Collider, and the difference between it and what came before it was not just one of scale or technology. The difference was a difference of ambition. The Large Electron-Positron Collider had accelerated electrons and their antimatter counterparts, the positrons. They are light particles, electrons. They are easy to push almost up to the speed of light. But they are easy to push for the same reason they are not the best probe of the underlying structure of matter. They radiate energy when you bend them around a circular path. The faster you push them, the more they bleed energy as synchrotron radiation, like a child shedding water from a too-full bucket. There is a practical ceiling to how far you can push an electron in a ring of a given size. To go further, to ask sharper questions of nature, you need a heavier particle. You need a particle that doesn't shed energy when you turn it. You need a proton. The Large Hadron Collider is a proton-proton machine. It takes hydrogen gas, strips the electrons from the hydrogen atoms, and accelerates the bare protons. Protons are nearly 2,000 times heavier than electrons. When you bend a proton around a circular track at relativistic speeds, the synchrotron radiation losses are vastly smaller. You can push a proton to enormously higher energies before the losses become prohibitive. The cost is that protons are not point particles. They are not the elegant little dots that electrons are. They are composite objects, made of three constituent quarks held together by the strong force, with a constantly shimmering cloud of gluons and quark-antiquark pairs flickering in and out of existence inside them. When two protons collide, what actually meets are pieces of protons, not protons. The collisions are messy in a way that electron-positron collisions are not. The physics that emerges from them is rich and complicated and requires enormous detectors to interpret. The protons inside the Large Hadron Collider do not travel as a single particle. They travel in bunches. Each bunch contains about 100 billion protons. The bunches are spaced out around the ring, with a typical separation of about 7.5 meters at full operation. There are typically 2,800 bunches circulating in each beam. Two beams travel in opposite directions through the same tunnel, in adjacent vacuum pipes, and at 4 points around the ring those pipes cross, and the bunches are squeezed and focused until they meet. The protons in those crossing bunches do not all collide. Most of them miss. But the geometry is engineered so that, at each crossing point, a few collisions happen every 25 billionths of a second. That is the heartbeat of the Large Hadron Collider. 25 nanoseconds. 40 million times a second, a new pair of bunches passes through each interaction point, and a new round of collisions starts. The detectors that watch those collisions are not small. There are 4 of them, each built in a vast underground cavern at one of the 4 crossing points around the ring. 2 of them are general-purpose detectors, designed to look at almost any kind of physics the collisions might produce. They are called ATLAS and CMS. ATLAS, which stands for a toroidal LHC apparatus, is the largest particle detector ever built by volume. It is 25 meters tall, 25 meters wide, 46 meters long. It weighs 7,000 metric tons. If you put it inside a cathedral, it would more or less fill the nave. CMS, which stands for the compact muon solenoid, is smaller in volume but heavier in mass. It weighs 14,000 metric tons, more than the Eiffel Tower. The third detector is called ALICE, a large ion collider experiment, and it is specialized for a different kind of physics. What happens when, instead of single protons, the collider accelerates whole lead nuclei and smashes them together? In those heavy ion collisions, the temperature and pressure at the collision point are so extreme that the ordinary structure of matter breaks down. Quarks, which inside protons are confined by the strong force and cannot exist on their own, briefly find themselves free, and the result is a state of matter called a quark-gluon plasma, which is thought to be the same state that filled the universe in its first microseconds. The fourth detector is called LHCb, the Large Hadron Collider Beauty Experiment, and it is designed to study one of the deepest open questions in physics: why the universe is made of matter and not antimatter. It does this by carefully observing what happens to particles containing what is called the beauty or bottom quark, looking for tiny asymmetries in the way matter and antimatter versions of those particles decay. The reason all of this matters for the story is that, in the spring of 2008, when Walter Wagner walked into the Honolulu courthouse, all of this had been built. The tunnel was finished. The magnets were installed. The detectors were complete, or nearly so. Final commissioning was underway. The first proton beams had not yet circulated, but the date for them was set. September of 2008. The first attempt at high-energy collisions was scheduled for the following weeks. The world's largest scientific experiment was, in physical fact, ready to begin. To make that experiment work, you have to do something remarkable to the magnets in the ring. There are roughly 1,200 superconducting dipole magnets, each 15 meters long, arranged end-to-end around the ring. Their job is to bend the proton beam. As the protons are accelerated to higher energies, they want, by Newton's first law, to fly off in a straight line. The magnetic field of the dipoles pulls them back into the curve of the ring. The higher the proton energy, the stronger the field has to be. At full run-3 operation, the dipole fields reach 8.3 Tesla. That is roughly 100,000 times the strength of the Earth's magnetic field. To generate fields that strong over 15-meter segments of beam pipe requires currents in the tens of thousands of amperes. To carry currents that high without resistive losses, the magnet coils have to be superconducting, made of niobium-titanium filaments embedded in a copper matrix. To make niobium-titanium superconduct, you have to cool it below its critical temperature, about 10 Kelvin. To get reliable operation with the right margin and the right field stability, the collider runs even colder than that. The temperature inside the Large Hadron Collider is 1.9 Kelvin. That is 1.9 degrees above absolute zero. In Celsius, it is roughly minus 271 degrees. The temperature of empty space far from any star is about 2.7 Kelvin, set by the residual heat of the cosmic microwave background. The Large Hadron Collider, when it is running, is colder than deep space. That is one of the more startling specifications of the machine, and it is not a poetic flourish. The cooling is achieved by surrounding the magnets with superfluid helium, helium that has been cooled below the lambda point, at which it loses its ordinary viscosity and begins to behave like an ideal heat conductor. The cryogenic plant that maintains this temperature is one of the largest in the world. It uses something like 120 metric tons of liquid helium. The cooling down process, from room temperature to 1.9 Kelvin, takes weeks. It cannot be rushed. The thermal contraction of 15-meter steel magnets at those temperatures is something the engineers have to plan for in millimeters of allowed shrinkage. When all of this is in place and operating, when the dipoles are at field, when the bunches are circulating, what is happening to the protons themselves? Each proton, in run 3, carries an energy of 6.8 tera-electron volts. The tera-electron volt is a unit physicists use because it is convenient for the energies involved at the high end of particle physics. 1 tera-electron volt is 1 trillion electron volts, which is the energy a single electron acquires if it falls through a potential difference of 1 trillion volts. 6.8 tera-electron volts is a remarkable amount of energy for a single proton to carry. When two protons collide head-on, their energies add. The total collision energy reaches 13.6 tera-electron volts. That is the number you hear quoted in CERN's press releases, 13.6 TeV. It is, at the time of writing, the highest controlled collision energy ever achieved by a particle accelerator on Earth. But energy by itself is not the most striking thing about a Large Hadron Collider proton. The most striking thing is the speed. To accelerate a proton to 6.8 tera-electron volts, you have to push it to a speed of 0.9999991 times the speed of light. Read those nines slowly. 6 of them, in a row after the decimal point, and then a 1. In absolute terms, the proton is moving about 3 meters per second slower than light. 3 meters per second. That is the speed of a slow walk. The difference between a proton in the Large Hadron Collider and a photon in free vacuum is the difference between a sprinter and someone strolling alongside them, and the sprinter is light, and the someone is the proton. In the time it takes you to blink, which is about 1/3 of a second, each proton has completed roughly 3,500 trips around the entire 27-kilometer ring. The numbers are difficult to picture because they were not built for picturing. They were built for nature. Nature does not have a problem with 3,000 laps per blink. It is only when humans try to describe it that the words begin to strain. There is a CERN analogy that is worth quoting, almost verbatim, because it captures the strange paradox of the energies involved. A single proton in the Large Hadron Collider carries about as much kinetic energy as a safety pin falling from a height of 2 centimeters. That is the analogy CERN uses, and it is a deliberate one. The energy, in everyday terms, is small, almost insultingly small. A safety pin falling 2 centimeters does not even register as an event in the world. You would not notice it. You would not flinch. But a safety pin, when it falls 2 centimeters, is a macroscopic object, and the energy is distributed across all of its atoms and all of its motion. A proton at 6.8 tera electron volts is a single particle, and the energy is concentrated in a region smaller than the proton itself, which is to say smaller than a femtometer, which is to say 1/4,000,000th of a meter. As in all of particle physics, the energy is not the whole story, the density of energy is. A safety pin falling 2 centimeters does nothing because it is spread out. The same energy, in a region a quadrillion times smaller, does the kind of thing that creates Higgs bosons. The Large Hadron Collider has in fact already done the kind of thing that creates Higgs bosons. On the 4th of July 2012, the Atlas and CMS collaborations announced in a packed auditorium in Geneva that they had observed a new particle with a mass of about 125 giga-electron volts. Within the following months, as the data accumulated, it became clear that the new particle was the Higgs boson, the last missing piece of the Standard Model, the particle whose existence had been predicted by Peter Higgs and his contemporaries in 1964, and the particle whose discovery completed a theoretical edifice that had been built brick by brick for half a century. It was, in every sense that matters in modern physics, an event of historic importance. The Higgs boson, in everyday language, is the particle responsible for the mechanism that gives mass to other particles. It is the reason the electron weighs what it weighs. It is the reason the W and Z bosons of the weak nuclear force are heavy enough to make weak interactions feeble. The fact that the Higgs exists, and that its mass is roughly 125 giga-electron volts, is the bedrock fact of contemporary particle physics. So when the lawsuit was filed in 2008, it was filed against a machine that, within 4 years, would announce the most important discovery in particle physics in a generation. The lawsuit's plaintiffs were not entirely wrong that the experiment they were trying to stop was unprecedented. They were wrong about what would happen at the end of it. What happened at the end of the first run was the Higgs. What did not happen then, or in the runs that followed, was anything that resembled the world ending. The world is still here. The Higgs is here too. The story of why that should be, why the world is still here, and what the Higgs has to do with the question Wagner and Sancho were really asking, is the story we have to tell next. It begins not with the machine, but with a piece of metal on a kitchen table, and it ends with a question about the weakest force in nature. Part 3. A paperclip and the deepest unsolved problem in physics. Here is something that should bother you more than it probably does. Pick up a small fridge magnet, the kind that you might use to hold a note to the door of your refrigerator. Hold it above a paperclip resting on a table. Bring the magnet slowly down. At some point, before the magnet has even touched the paperclip will jump. It will leap upward, off the surface of the table, and stick to the magnet. You will not be surprised. You have seen this happen 100 times. It is the kind of thing children play with. You will not in the moment think it is strange, but it is. It is one of the strangest things in physics, and the strangeness of it is something most people walk past without noticing. A paperclip jumps to a magnet against the entire pull of the planet. Think about that for a second. Think about what just happened. Beneath the paperclip is the Earth. Not a small object, not a casual object. A ball of rock and molten iron and ice and ocean and atmosphere, 6,000 kilometers deep at its center, with a mass of about 6 trillion kilograms. That entire object, with its entire mass, is pulling on the paperclip. every atom of the planet is reaching upward, gravitationally, toward every atom of the paperclip, telling it to stay. And above the paperclip is a small piece of magnetized iron, the size of a coin, weighing less than 10 grams, and the small piece of magnetized iron wins. The paperclip leaves the table, the planet loses. This is not a quirk. It is not a peculiarity of magnets, or of paperclips, or of small fridge experiments. It is a feature of every interaction in nature. The force that holds galaxies together, that curves space-time, that gives the universe its overall shape, that pins each star in its orbit and each planet to its star and each moon to its planet, is, by an almost unbelievable margin, the weakest of the 4 fundamental forces that physics has identified. It is weaker than our electromagnetism. It is weaker than the strong nuclear force that holds the inside of every atomic nucleus together. It is weaker than the weak nuclear force that is responsible for certain kinds of radioactive decay. It is weaker than all of them. And it is not weaker by a little. It is weaker by an amount that defies ordinary intuition. Between 2 electrons, the electromagnetic repulsion is roughly 10 to the 42nd power, times stronger than the gravitational attraction. Read that number slowly, 10 to the 42nd, 1 followed by 42 zeros. The strong nuclear force, the one that holds the quarks inside each proton and neutron together, is stronger than gravity by an even larger factor, when you measure it at the right scale. Even the weak nuclear force, the one that is itself called weak, because it is shorter ranged and feebler in everyday terms than electromagnetism, is far stronger than gravity at the scales where it operates. Gravity is, in every fair comparison, the runt of the 4, and the strangeness of this is that it is not a small effect that becomes negligible at small scales. It is a vast, persistent, deeply seated structural fact about the universe. The universe is built such that the force that shapes its larger structures is, when you get down inside an atom, almost imperceptible compared to the forces operating there. Physicists have a name for the puzzle this presents. They call it the hierarchy problem. The name is dry. It does not give the puzzle the drama it deserves. The puzzle, written out properly, sounds like this. The weak nuclear force, which is responsible for radioactive decay, operates at an energy scale of about 100 giga-electron volts. The particles connected to that force, the W and the Z bosons that carry the weak interaction, the Higgs boson that gives them their mass, all sit at masses in roughly this range. 100 giga-electron volts is the natural energy scale of weak interaction physics. It is the scale where the W and the Z live, where the Higgs lives, where the symmetry breaking that distinguishes the weak force from electromagnetism happens. It is the scale that the Large Hadron Collider was specifically designed to explore. But there is another scale in physics. It is called the Planck scale, after the physicist Max Planck who first identified it in 1900. The Planck scale is the scale at which gravity, in the standard 4-dimensional picture, becomes comparable in strength to the other forces. It is the scale at which the smooth fabric of general relativity is supposed to give way to whatever the deeper quantum theory of gravity actually is. The Planck energy is roughly 10 to the 19th giga-electron volts. That is 1 followed by 19 zeros, then giga, then electron volts. To express how far that is from the weak scale, you need scientific notation. The ratio of the Planck scale to the weak scale is roughly 10 to the 17th, 17 orders of magnitude. If you write out 17 orders of magnitude on a strip of paper, you will need a strip about as long as a meter to fit all the zeros at any reasonable handwriting size. If you imagine 17 orders of magnitude as a physical distance, with the smallest scale you can think of at one end, you cross most of the visible universe before you reach the other end. The ratio between the smallest things humans can resolve and the size of the observable universe is, by comparison, only about 35 orders of magnitude. 17 orders of magnitude is, in any honest accounting, a very large number, and it is not the size of something physical. It is the size of the gap between 2 scales of energy that, on its face, ought to be of order 1 to each other. Why is the weak scale not 10 to the 19th giga-electron volts? Why is the Higgs mass not 100 billion times what we actually measure? That is the hierarchy problem. There is an additional twist to the puzzle that makes it feel even more urgent, because it is not just that the 2 scales are different. Quantum field theory predicts that the Higgs boson, in the absence of any new physics, should not be light. The Higgs is a scalar particle, and scalar particles in quantum field theory do not have natural protection from large quantum corrections to their mass. Every virtual particle that briefly comes into existence and interacts with the Higgs contributes a correction to its mass. Most of those corrections are positive, in the sense that they push the Higgs mass upward, and most of those corrections are enormous, because the integrals that compute them, when you take them all the way up to the highest energies in the theory, give you mass corrections of order the cutoff of the theory. If the theory is valid up to the Planck scale, the corrections are of order the Planck scale. The Higgs, naively, should be of order 10 to the 19th giga-electron-volts. It is not. The Higgs, as measured by ATLAS and CMS in 2012 and refined in the years since, sits at about 125 giga-electron-volts. For that to be the case, the various contributions to the Higgs mass, the positive corrections from virtual particles, the negative corrections from supersymmetric partners if they exist, the bare mass term in the Lagrangian, would have to cancel each other out to extraordinary precision. To get a Higgs mass at 125 giga-electron-volts, when individual contributions are of order 10 to the 19th, you need a cancellation that is accurate to about 1 part in 10 to the 34th. That is the same kind of precision as balancing a stack of pennies on a needle so accurately that, after the entire age of the universe, the stack still does not fall over. It is not the kind of thing that happens by accident in nature. When physicists see a cancellation like that, they do not say, "Oh, how lucky! The universe just happens to balance to 34 decimal places." They say something must be doing that. Something must be protecting the Higgs mass from being pulled up to the Planck scale. Something we have not yet found. This something has a generic name. It is called naturalness. The principle of naturalness, in the form physicists have used it for the last 50 years, says that dimensionless ratios in nature should be of order 1, unless there is a reason, some symmetry or some structure or some new physics, that suppresses them. A ratio of 1 part in 10 to the 34th with no protection is the antithesis of naturalness. It is the kind of thing that, if you found it in a fundamental theory, would convince you that you were missing something. For most of the last 40 years, the dominant guess about what we were missing was supersymmetry. Supersymmetry posits, in its simplest forms, that every particle in the standard model has a heavier partner of opposite statistics. Every fermion has a bosonic partner, every boson has a fermionic partner. If those partners exist and are not too much heavier than the Higgs, their quantum contributions cancel the large corrections from their standard model counterparts, and the Higgs mass is kept naturally light. Supersymmetry was the favourite for so long that it had its own jargon, its own diagrams, its own experimental searches built specifically to find it. The Large Hadron Collider was, in addition to being the Higgs factory, designed to be the supersymmetry discovery machine. It has not found supersymmetry. The simplest, most economical, most natural versions of supersymmetry, in which the partner particles are within a couple of TeV of the Higgs mass, have been thoroughly searched and not found. The lower bound on the masses of the squarks and the gluinos and the various other superpartners is now well above a TeV, in many cases well above 2 TeV, in many cases pushing into the territory where the supersymmetric explanation of the hierarchy problem starts to require fine-tuning of its own. The favourite has been demoted. Supersymmetry is not dead. It may still be there, at higher scales than the LHC can reach. But the most beautiful, most natural version of the story is, by an increasingly tight margin, falsified. This is the conceptual ground on which the lawsuit was, in retrospect, asking its question. Wagner and Sancho did not phrase it this way. They were not worried about naturalness. They were worried about black holes. But the reason a black hole at the LHC was even a thing anyone could mention with a straight face was that the hierarchy problem had become, by the late 1990s, urgent enough that people were willing to consider radical solutions. One of those radical solutions, the most radical of them, was that maybe gravity is not actually weak at all. Maybe gravity only looks weak. Maybe the 17 orders of magnitude between the weak scale and the Planck scale are not real. Maybe the Planck scale is actually right there, just above the weak scale, just at the edge of what an experiment like the Large Hadron Collider could probe. Maybe what looks like a desert of 17 empty orders of magnitude is actually a stage curtain, and what looks like nothing on the other side is actually a whole hidden room, with the rest of physics in it. That is the proposal we have to look at next. The paperclip, when you bring the magnet near it, is not just jumping, it is testifying. It is telling you, in the most ordinary kitchen table experiment you can perform, that the universe is built strangely. The strangeness of it is the deepest open problem in fundamental physics, and the lawsuit in its way was a clumsy demand that someone notice. Part 4. A 1998 paper that punched a hole through that reasoning. The proposal we have to look at was published in 1998 in a paper that did not, at the time, look like the kind of paper that would, a decade later, end up implicated in a courtroom drama. The authors were three theorists. The first was Nima Arkani Hamed, then a postdoctoral researcher at Stanford. The second was Savas Dimopoulos, also at Stanford. The third was Gia Diwali, then at the International Centre for Theoretical Physics in Trieste. The paper appeared in the journal Physics Letters B in the spring of 1998, and its title was disarming for how mundane it sounded compared to what it proposed. The paper was called The Hierarchy Problem and New Dimensions at a Millimeter. The paper has come to be known, in the years since, as the ADD model, after the initials of its authors. It is one of the most cited papers in modern theoretical physics. And the reason it is one of the most cited papers is that it asked one question, in one sentence, that had the property of being either completely wrong or completely transformative. There was very little possibility of it being only slightly correct. The question was this: what if gravity is not actually weak? What if gravity only looks weak because we are not seeing all of it? The framework Arkani Hamed, Dimopoulos and Diwali built around that question goes like this. Suppose, they said, that the universe has more than 3 spatial dimensions. The familiar 3, the up and down, side to side and front to back of everyday experience, are not the whole story. There are additional spatial dimensions beyond the 3, but those additional dimensions are not infinite like the ones we're used to. They're compactified. They're curled up, folded in on themselves so tightly and so cleanly that no experiment we have ever conducted has resolved them. They are, in the literal geometric sense, too small to see. The size of the additional dimensions in their original proposal could have been as large as a millimeter, hence the title of the paper. The reason the millimeter scale was interesting was that at that time, experimental tests of Newton's inverse square law of gravity at very short distances were just beginning to be able to probe down to millimeter scales. If the additional dimensions were a millimeter or so in size, gravity at sub-millimeter distances would not follow the inverse square law of three-dimensional gravity. It would follow a different law, steeper and stronger. The Yertwash experiments at the University of Washington and similar tests around the world have, in the years since, pushed those limits down to micron and even sub-micron scales, ruling out the original ADD proposal in its most generous form. But the framework, even with the sizes pushed smaller, has retained its theoretical interest because the central idea survives. The central idea is that the particles of the standard model, the quarks and the electrons and the photons and everything else that makes up ordinary matter, are confined to a three-dimensional surface inside the higher dimensional space. This surface is called a brane, after the word membrane, because it is like a membrane in fluid mechanics, a lower dimensional structure embedded in a higher dimensional volume. The standard model particles cannot leave the brane, they can move along it, they can interact with each other on it, but they cannot escape into the surrounding higher dimensional bulk. The forces they feel, electromagnetism, the strong force, the weak force, are all confined to the brane. From their perspective, the brane is the entire universe. The bulk does not exist because they have no way to interact with it. Gravity is different. Gravity, in general relativity, is not really a force in the same way that electromagnetism is a force. Gravity is the curvature of space-time itself, and there is no reason, in principle, that the curvature of space-time should be confined to the brane. Gravity, in the ADD picture, is the one thing that can leave the brane. Gravity spreads into the bulk. It propagates in all of the dimensions, not just the 3 we live in, and because it spreads, it gets diluted. Most of its strength, at any given distance from a source, is leaking sideways into the extra dimensions, where we have no way to observe it. The 4-dimensional gravity we measure on Earth is only a fraction of the total. It is the residue. It is what is left after the bulk of the gravitational flux has bled into directions we cannot see. Picture yourself looking at a thin sheet floating inside a large tank of water. The sheet is perfectly flat, perfectly horizontal, suspended in the middle of the tank. You take a small bottle of brightly coloured dye and you tilt it carefully, letting a single drop fall onto the surface of the sheet. The drop lands. The dye begins to spread. It moves out across the surface of the sheet in a slow, branching pattern, like ink on wet paper, finding the contours of the surface and following them. But the dye does not enter the water around the sheet. The sheet is impermeable to the dye in both directions, and so the dye is trapped on the surface, spreading only sideways, only in the 2 dimensions of the sheet itself. Imagine now that there are creatures living on the sheet. They are very small. They are so small that the sheet, for them, is the whole world. They have lived on it their whole lives. They have no way to perceive the water above or below them. They study the dye. They make theories about how it spreads. They write papers about its diffusion. From their perspective, the dye is one of the few things they can see, and the geometry of their world is the geometry of the sheet. Now somebody taps the side of the tank. A wave propagates through the entire volume of water. The wave moves above the sheet, below the sheet, and through the sheet, because water can move through water. The sheet, having a small but finite mass, is disturbed by the wave. It rocks gently, briefly, as the wave passes. The dye on its surface ripples. The tiny creatures who live on the sheet feel something. They feel a faint shudder, a barely detectable disturbance in the geometry of their world. They look at it with their instruments. They measure its energy. They find it tiny, vanishingly small compared to anything else they have measured. They write papers about it. They puzzle over its weakness. Some of them propose that the disturbance is a fundamental new force, weaker than the others by some enormous factor. They cannot understand why. They have no way to know that the wave, the real wave, the wave that they have detected only a fraction of, was actually enormous. Most of its energy has dispersed through the water above and below them, in directions they were never built to perceive. The wave was not weak, they were just unable to see most of it. That is the analogy the ADD authors used, and that has been used and reused by every popular description of their work since. The sheet is our universe, the 3-dimensional brain we live on. The dye is ordinary matter, atoms and light and quarks, confined to the brain. The water surrounding the sheet is the higher dimensional bulk. The wave is gravity. If the picture is correct, the weakness of gravity is not a fundamental property of nature. It is a geometric artifact. It is what you get when you measure the strength of an interaction that is spreading into directions you cannot see, using instruments confined to the directions you can. The mathematical consequences of this idea are precise. In ADD, with n extra dimensions of size r, the relationship between the 4-dimensional Planck mass m Planck, which is what we measure as the strength of gravity in our world, and the true fundamental Planck mass m fund, which is the actual gravitational coupling in the higher dimensional theory, is given by a clean formula. M Planck squared equals m fund to the power of n plus 2 times r to the power of n. Translated into less mathematical language, this means that if you have enough extra dimensions of a large enough size, the true fundamental Planck mass can be much smaller than the 4-dimensional Planck mass we measure. With 6 extra dimensions of an appropriate size, the true fundamental Planck mass can be brought all the way down to about 1 TeV, right there, right at the energy scale of the Large Hadron Collider. If that were the case, the 17 orders of magnitude between the weak scale and the Planck scale would simply not exist. The desert would not exist. The hierarchy problem would not exist as we have come to know it. The reason gravity looks weak would be the geometric leakage we just described. The reason no machine on Earth has ever come close to creating a black hole would be that no machine before the LHC was operating at energies where the true gravity was relevant. The reason black holes seem like the exclusive property of dead massive stars and the centres of galaxies would be that the gravity we know is the diluted shadow of the gravity that actually governs nature at short distances. And the question of whether a collider could create a microscopic black hole would no longer be ridiculous. It would be a question of energy and geometry, and the energy and geometry would, for the first time in history, be inside the reach of an experiment. The ADD paper was published in 1998. The Large Hadron Collider was already under construction. The collision energies the collider was designed to reach, initially 7 TeV, eventually 13 TeV, then 13.6 TeV in run 3, sat right at the scale where, in the ADD picture, the true Planck mass might be. It was not a coincidence, it was an observation. Arkani Hamed, Dimopoulos, and Diwali knew exactly what was being built. Their paper, in a quiet way, was an invitation to look. If the universe is structured the way they were proposing, the Large Hadron Collider will not just be a machine for making Higgs bosons and producing exotic particles. It will be a machine for testing whether gravity is weak, and if gravity is not weak in the way ADD proposes, the experiment will say so. It will say so by producing, or by failing to produce, microscopic black holes. The lawsuit in 1998 did not yet exist. The lawsuit's filing was still a decade away, but the conceptual ground for the lawsuit was being laid, in plain sight, in a peer-reviewed journal in physics. 3 theorists at 3 different universities had written down, in equations, a possibility that, if true, would make the Large Hadron Collider a black hole factory. The lawsuit's instinct was wrong about almost everything. It was wrong about the timeline. It was wrong about the danger. It was wrong about the probability. But it was not wrong that, somewhere in the published literature, a serious proposal was waiting to be tested. The proposal was ADD. The test was the Large Hadron Collider. And the next step, the step that bridged the theory to the experiment, was a second paper, 3 years after ADD, that did the cold calculation of what would actually happen. Part 5. Black Holes at the LHC. In the spring of 2001, Savas Dimopoulos, one of the original 3 authors of the ADD proposal, sat down with another theorist, Greg Landsberg, then at Brown University, and worked through what the ADD framework would actually mean for an experiment at the energy of the Large Hadron Collider. The paper that came out of that collaboration was titled, with a directness that did not soften the implications of its content, Black Holes at the LHC. It appeared in the journal Physical Review Letters. The title alone was the kind of thing that, if you saw it on the cover of a journal, you had to read at least the abstract. The abstract said, in calm technical language, that if the ADD framework were correct, the Large Hadron Collider would be a copious factory for microscopic black holes. The numbers in the body of the paper said that, at full design luminosity, the collider could produce up to about 1 black hole per second. To understand how Dimopoulos and Landsberg arrived at that number, you have to understand a strange and important fact about protons. A proton is not a point. A proton, in the careful language of particle physics, is a composite object. Its inside is busy. It is not 3 quarks sitting placidly together, even though that is how introductory textbooks draw it. It is 3 valence quarks, 2 ups and a down, surrounded by a turbulent cloud of gluons holding them together with the strong force, and within that cloud, at any given instant, a virtual ferment of quark-antiquark pairs popping in and out of existence. The 3 valence quarks carry the proton's overall identity, its charge, its baryon number, its general structure, but they do not carry all of its energy. Most of the proton's energy, at high momentum, is actually carried by the gluons and the virtual quark-antiquark pairs, collectively called the partons. When 2 protons collide head-on at the Large Hadron Collider, they do not collide as 2 single particles meeting at a point. They collide as 2 complicated bags of partons, each parton carrying some fraction of the proton's total energy, each parton moving more or less parallel to the proton's direction of motion. What actually happens, at the most fundamental level, is that 1 parton from 1 proton meets 1 parton from the other proton, and those 2 partons interact. The rest of the proton, the partons that did not happen to participate, continue down the beamline as fragments. The interaction itself happens between 2 pieces of 2 protons, with a centre of mass energy that depends on what fraction of the proton's total energy each parton happened to be carrying. The available energy in the parton-parton collision is, on average, smaller than the full 13.6 TeV of the proton-proton collision. But it can range up almost all the way to the full energy if both partons happen to be carrying most of their respective protons' energy at the moment of impact. Most of the time, the parton-parton interaction is uninteresting. The partons exchange momentum, produce a spray of new particles, and the result is the kind of event that the Standard Model has been predicting for decades. The Large Hadron Collider produces these uninteresting events trillions of times per day. They are the bread and butter of the experiment, the calibration data, the background against which any new physics has to be searched. But occasionally in the ADD picture, the partons can do something more dramatic. They can pass close enough to each other that the energy they're carrying is concentrated inside an extremely small region, and in the ADD picture, that small region might be small enough to matter gravitationally. The relevant length scale is called the Schwarzschild radius, after the German physicist Karl Schwarzschild, who derived it from Einstein's equations in 1916. The Schwarzschild radius of an object is the radius at which, if you compressed the object's entire mass energy inside it, an event horizon would form. An event horizon is the boundary of a black hole. It is the surface from which, in classical general relativity, no signal, not even light, can escape to the outside. For an object the mass of the Earth, the Schwarzschild radius is about 9 millimeters. For an object the mass of the Sun, it is about 3 kilometers. For an object the mass of a proton, the Schwarzschild radius is so absurdly small, about 10 to the minus 54 meters, that you cannot use any ordinary words to describe it. It is many, many orders of magnitude smaller than the proton itself. In ordinary four-dimensional gravity, the energies of the LHC are not even close to forming a black hole, because the Schwarzschild radius corresponding to those energies is many, many orders of magnitude smaller than the distance scale of the collision itself. But the ADD framework changes the Schwarzschild radius. In a higher dimensional gravitational theory, the formula for the Schwarzschild radius does not depend on the four-dimensional Newton's constant. It depends on the fundamental higher dimensional gravitational coupling, which in the ADD picture is set by a Planck mass of around 1 TeV rather than 10 to the 19th GeV. The Schwarzschild radius scales differently with the number of dimensions, and the absolute values come out much larger than the four-dimensional formula would suggest. For a few TeV black hole in AD-style gravity, the Schwarzschild radius works out to be of order 10 to the minus 19th meters. That is the size of an atometer, which is 1/1000th of a meter. It is still very, very small. It is smaller than a proton by a factor of about 10,000. But it is not zero. It is not unreachably small. It is, in the ADD picture, the kind of scale that two energetic partons could plausibly bring their mutual center of mass energy inside. The mechanism is easier to picture than the math suggests. Two protons collide head-on. Inside them, two partons happen to be moving toward each other with very high energies. By chance, those two partons pass within an atometer or so of each other at the moment they cross. The energy between them, packed into that tiny volume, exceeds the threshold for horizon formation in higher dimensional gravity, and space-time cannot decline. Once the geometry is met, the horizon forms. The result is a microscopic black hole. That phrase, space-time cannot decline, is worth holding for a moment. It is, in the ADD picture, the simplest description of what is happening. In general relativity, the formation of an event horizon is not optional. If you concentrate enough energy in a small enough region, the geometry of space-time has no choice. It must curve into the configuration we recognize as a black hole. The phrase is not poetic. It is descriptive of the equations. Once you put the energy inside the radius, the horizon is the inevitable consequence of the laws of gravity as Einstein wrote them down. The peculiarity in the ADD picture is just that the radius is reachable. The energies are reachable, and so the formation of the horizon is reachable. Dimopoulos and Landsberg's paper worked out the production cross-section, the probability per collision for a black hole of a given mass to form in this way. They used a remarkably simple physical argument. The cross-section for two partons to form a black hole of mass m is approximately the area of a disk, with radius equal to the higher dimensional Schwarzschild radius for that mass. They calculated, for the LHC's design luminosity and the parton energies available, what the total black hole production rate would be. The result was that, if ADD with the right parameters were correct, the LHC would produce on the order of 1 black hole per second. The masses of these black holes would range from a couple of TeV up to a maximum of about the full collision energy, which is to say maybe 10 or 12 TeV. The mass of a few TeV is, in the units of everyday life, almost nothing. It is roughly 10 to the minus 23 grams, a trillionth of a gram, smaller than the proton that made it, smaller than anything we ordinarily call a particle. This is a place where a certain instinct needs to be switched off. The phrase black hole pulls images from somewhere deep in the imagination. The black hole at the center of our galaxy, Sagittarius AE, 4 million times the mass of the Sun. The dark body at the core of Cygnus X1, a stellar mass black hole whose presence was inferred from the X-ray emission of its companion star. the supermassive monster at the heart of M87, the one whose silhouette was imaged by the Event Horizon Telescope and unveiled in 2019. Those are all objects with enormous masses, enormous gravitational pulls, enormous influence on the matter around them. None of that applies to a microscopic black hole in the ADD picture. A stellar mass black hole has the gravitational pull of a star. A supermassive black hole has the gravitational pull of billions of stars. A microscopic black hole at the LHC would have the gravitational pull of a grain of dust. Less than that. A few TV is, in mass terms, an unmeasurable speck compared to anything in our experience. Its event horizon, if it formed, would be smaller than a proton. Its gravitational reach, beyond that horizon, would be utterly negligible at any distance you can imagine. But the calculations said it would form. The lawsuit's intuition, in retrospect, had the wrong picture in mind. The lawsuit was imagining a small Sagittarius A, a tiny version of the galactic monster, dropped into the underground tunnel and beginning to feed. The actual proposal, from the actual theorists, was the production of objects so light and so small that the words black hole almost stop applying to them in any way that connects to popular intuition. The objects in question would be, in their own way, the most delicate things the universe had ever produced. The most delicate things, but still inevitable. Because once the geometry was met, space-time could not decline. The Demopoulos and Landsberg paper hit the theoretical physics community like a wave. It was beautiful. It was clean. It made a sharp, falsifiable prediction. Either the Large Hadron Collider would, when it switched on, produce microscopic black holes in abundance, in which case the deepest open problem in physics, the hierarchy problem, would be solved in a way nobody had quite dared hope for, or it would not. If it did not, the simplest, most beautiful version of ADD would be ruled out decisively by the absence of an effect that was supposed to be there. There was no middle ground. There was no slightly correct version of the theory. There was either a flood of black holes, or there was nothing, and the question of which one would be answered by an experiment that was, in 2001, already being built. The Hawaii lawsuit was filed 7 years later. By then, the prediction was a familiar idea in physics. The lawsuit's plaintiffs had read about it, or read about reports of it, or read about reports of it. They had been frightened. They had not, perhaps, read all the way through to the next part of the story. The next part of the story is what was supposed to happen to one of those black holes, if it did form, the moment after it was born. The next part of the story is what Stephen Hawking had worked out in 1974. The next part of the story is the reason the lawsuit was answering itself before its first hearing. Part 6. The Horizon That Lasts. 10 to the minus 27th of a second. The image we carry of a black hole is a mouth, something that swallows, something that grows on whatever it touches. This is the picture the Hawaii lawsuit was leaning on. A horizon opens, matter falls in, the thing gets larger. Eventually it gets large enough to sink through the crust of the planet and begin devouring the Earth from the inside out. This picture is, in the lawsuit's frame, the natural and obvious thing to assume. Black holes, in popular imagination, eat. The thing about them is that they eat. They are defined, in stories, by what they take. Any object that has formed an event horizon, the imagination concludes, will continue to grow as long as there is matter near it. The only question, in the lawsuit's reasoning, was whether there would be enough time to do something about it before the horizon reached a size at which nothing could be done. Stephen Hawking killed this picture in 1974. He did it by applying quantum field theory to the curved space-time around a classical black hole, in a calculation that was, at the time, unfashionable and difficult, and almost universally regarded as a curiosity. Hawking was working at Cambridge. He had been interested in black holes for years, and he had begun to wonder what would happen if you took the quantum vacuum, the bubbling sea of virtual particle pairs that fills empty space according to quantum field theory, and put it next to an event horizon. The vacuum, in flat space-time far from any gravitational source, is in a particular state. It looks empty. Virtual particle-antiparticle pairs are constantly appearing and annihilating, but they cancel each other out, and the average energy density of the vacuum is what it is, small but not zero. The vacuum near a black hole, Hawking realized, does not have the same properties as the vacuum far away. The horizon distorts the boundary condition. The virtual pairs, in the strong gravitational field at the edge of a horizon, do not always cancel each other out. One member of the pair can fall through the horizon, and the other can escape to infinity. The escaping member, from the perspective of an observer far away, looks like a real particle being emitted by the black hole. The calculation is one of the most beautiful in modern physics. Hawking showed that when you carry through the consequences of quantum field theory in the geometry of a black hole, the hole emits a spectrum of particles that is precisely thermal. It glows like a hot body, with a temperature inversely proportional to its mass. The radiation is universal. It includes every kind of particle the standard model contains, in the proportions that a thermal blackbody would emit them. The radiation carries energy away. The black hole, as a consequence, must lose mass to compensate for the energy it is emitting. Black holes, Hawking concluded, are not permanent. They are slowly evaporating. Over enormous timescales, even the most massive black hole in the universe will, in principle, radiate itself away, until at the end of its life it has shed almost all of its mass, and the final dregs of it explode in a brief, intense flash. For ordinary astrophysical black holes, this evaporation is unimaginably slow. The temperature of Hawking radiation from a stellar mass black hole is about 100 nanokelvin, far colder than the cosmic microwave background, which means that such a black hole, sitting in the universe today, is absorbing more radiation from its environment than it is emitting. It is, on net, gaining mass, not losing it. The temperature for a supermassive black hole is even lower. The evaporation timescales for ordinary black holes are vast beyond imagination. A stellar mass black hole would take about 10 to the 67th years to evaporate completely. A supermassive black hole would take 10 to the 100th years or more. These are timescales that dwarf the current age of the universe, which is a relatively youthful 10 to the 10th years. But the rule cuts the other way than intuition suggests, and this is the part that matters for the lawsuit. Smaller black holes are hotter. Smaller black holes radiate more fiercely, not less. The temperature is inversely proportional to the mass, which means that as a black hole gets smaller, it gets hotter, which means it radiates faster, which means it shrinks faster, which means it gets hotter still. The evaporation accelerates. The endpoint for any black hole is not a slow fade. It is an exponentially accelerating burn that, in the final fractions of its lifetime, becomes a flash. A black hole the mass of a mountain would glow brightly. A black hole the mass of an asteroid would burn intensely. A black hole the mass of a proton would not evaporate. It would detonate. A microscopic black hole at the Large Hadron Collider, carrying a mass of a few TeV, sits at the extreme end of this scale. Its Hawking temperature would be enormous, of order a TeV in energy. Its lifetime, calculated from the Hawking formula, would be roughly 10 to the minus 27th of a second. Picture yourself watching a single proton-proton collision inside the Atlas detector. Slow it down, slow it more, slow it to a stop. The two protons are approaching each other at almost the speed of light, with 13.6 TeV of total centre of mass energy. Inside each proton, the partons are moving. Two of them, on a chance trajectory, are about to pass close enough to fold space-time around themselves. You can see in your mind's eye the geometry tightening, the energy concentrates. The Schwarzschild radius for the parton-parton system is roughly an automator, and the partons are inside it. Space-time cannot decline. A horizon forms. It is the smallest horizon that has ever existed in this region of the universe. It is smaller than the proton that carried the partons. It is smaller than anything we would ordinarily call a particle. But it is, in the brief moment of its existence, an event horizon, a real one, a piece of geometry that, in the equations of general relativity, divides the universe into inside and outside. You watch the next 10 to the minus 27th of a second. It is not enough time for light to cross the proton that produced the horizon. It is not enough time for any signal to travel between the constituent partons of the proton. The black hole begins immediately to radiate. The temperature is so high that the radiation includes every kind of particle the standard model has. Quarks of all flavours, leptons of all flavours, photons, gluons, W and Z bosons, the Higgs boson itself, all streaming outward from a single point with energies of order a TeV each. The radiation is quasi-spherical, emerging in all directions roughly equally. The mass of the black hole drains away as the radiation carries it off. The radiation as it leaves gets hotter because the black hole is shrinking. The shrinking accelerates, the radiation peaks, and then there is no black hole. There is only the radiation. There is only a burst, a fireball of particles spreading out into the rest of the detector, looking nothing like an ordinary collision in its multiplicity and its symmetry and its total transverse energy. The horizon is already gone. By the time the detectors notice anything at all, the object that was a black hole has finished. There is no time for it to drift, no time for it to fall, no time for it to grow. Its lifetime was so short that even the concept of motion through space barely applies to it. It appeared and finished, and the next collision happens 25 billionths of a second later, which compared to the lifetime of the black hole is itself an age. The detector records the spray of particles. The trigger system flags the event for further analysis. The data eventually will be written to tape. The black hole, if it ever existed in the way Dimopoulos and Landsberg predicted, will be entirely a thing of the past tense. This is what Hawking's calculation says will happen in the cleanest interpretation of the ADD picture. The black hole, if it forms, is gone in 10 to the minus 27th of a second. It does not drift toward the centre of the Earth. It does not accrete matter. It does not grow. It evaporates almost instantly into a spray of particles that the detector sees as a single, peculiarly democratic, peculiarly high-energy event. That is the signature the experimenters were instructed to look for. That is the signature that, if it ever appeared in the LHC's data, would mean that ADD was right, and the hierarchy problem had been solved by extra dimensions, and the lawsuit's instinct that something dramatic was about to happen at the energy frontier of physics had been, in a strange way, vindicated. There is an honest caveat to place on all of this. Hawking radiation has never been directly detected. Nobody has watched a black hole evaporate. Nobody has caught the radiation coming off one. The prediction is theoretical, built from the application of quantum field theory to curved space-time, and almost every working physicist accepts that the calculation is correct. But acceptance is not observation. The LHC Safety Assessment Group, in its independent report, said as much, openly, in 2008. The report did not pretend Hawking radiation had been confirmed. It walked through the physics carefully and acknowledged the gap between what had been calculated and what had been observed. If the Hawking argument had been the only thing standing between the world and the lawsuit's scenario, there might have been room for the faintest doubt. It is not the only thing. The second argument is older than Hawking's calculation, older than the LHC, older than the ADD paper. The second argument is written in the sky. Part 7. The sky has already run the experiment. Every second of every day, the Earth is struck by particles from space. Protons and atomic nuclei, accelerated by some of the most violent processes in the universe. Supernova shocks, the jets of active galactic nuclei, the accretion disks of supermassive black holes, arrive at the top of the atmosphere with energies ranging from millions of electron volts up to numbers that, when you write them down, look more like astronomical observations than particle physics measurements. They are called cosmic rays. They have been arriving in roughly the same flux for the entire history of the planet. They are not a feature of any one telescope or any one experiment. They are a feature of the sky. Most cosmic rays are not extraordinarily energetic. Most of them carry energies that are easily within the reach of Earth-based accelerators, including in some cases modern colliders. But the spectrum of cosmic rays extends to enormous energies. The flux at the high end is rare, but it is not zero. The Pierre Auger Observatory in Argentina and the Telescope Array Project in Utah have, over the last 2 decades, recorded events at energies above 10 to the 20th electron volts. These are particles carrying as much kinetic energy as a small object falling from a table, packed into a single proton or nucleus. They arrive, on average, at a rate of about 1 per square kilometer per century, above 10 to the 20th electron volts. Rare, but not absent. In October of 1991, an event was recorded by the Fly's Eye experiment at the Dugway Proving Ground in the Utah desert. The Fly's Eye was an array of detectors that watched the night sky for the fluorescent flashes produced when ultra-high energy cosmic rays strike the upper atmosphere and produce showers of secondary particles. On the night of October 15th, one of those flashes was unusually bright. The reconstruction of the shower when the data was analysed gave an estimated energy for the original particle of about 3 times 10 to the 20th electron volts. In the units, particle physicists use for the Large Hadron Collider, this is about 320 million TeV, tens of millions of times more energetic than any collision the LHC has ever produced, tens of millions of times more energetic than any collision the LHC will ever produce, even at the highest design luminosity. The particle was given a nickname by the team that detected it and by the physics community that absorbed the news in the months that followed. It came to be known as the Oh My God particle. It was, at the time, the highest energy particle ever recorded. It remains one of the highest energy particles ever recorded, though several events of comparable or near comparable energy have been detected since. The interesting fact about the Oh My God particle, for the purposes of the story we're telling, is not that it set a record. The interesting fact is that it was one event in one detector, in one desert, in one country, on one particular October evening. The rest of the sky was full of similar events all the time. The Earth was being bombarded continuously, every second of every day, by cosmic rays whose energies, individually and collectively, dwarf anything humans have built. These cosmic rays do not just strike the Earth. They strike the Moon, which has no atmosphere to slow them down before they hit the surface. They strike the Sun, which is dense but extended. They strike Mercury and Mars and the gas giants and the moons of the gas giants. They strike asteroids and comets and dwarf planets in the outer solar system. They strike the surfaces of neutron stars, which are the densest matter in the observable universe. They strike the surfaces of white dwarfs, which are the second densest. They have been doing this in some cases for billions of years. The Moon has been a stationary cosmic ray target for 4.5 billion years. The Sun, similarly. Neutron stars, when they form, become almost immediately the bullseye for cosmic ray bombardment, and they have been the bullseye for as long as they have existed. Stefan Kutu, a physicist at Penn State, put the argument in about as plain a sentence as physics permits. If cosmic ray collisions could create black holes that would swallow the Earth, it would have happened already. The line is almost dismissive in its simplicity, and that is the point. The cosmic ray defense of the LHC is not a clever argument. It is not a subtle calculation. It is an observation. The sky has been doing the lawsuits experiment for 4 billion years. The Earth is here. The Moon is here. The Sun, Mercury, Mars, Jupiter, Saturn, Uranus, Neptune, all the moons and rings and asteroids and trans-Neptunian objects, all still here. The Crab Nebula, with its pulsar at the centre, pumping out cosmic rays in all directions, is still a stable structure. The neutron stars in binary systems, where cosmic ray bombardment is even more intense, are still neutron stars. None of them have been converted into black holes. None of them have been consumed from within by hidden gravitational objects produced in their atmospheres. Stand outside on a clear night and look up. The stars you can see, every one of them, has been struck for as long as it has existed by particles tens of millions of times more energetic than anything the Large Hadron Collider has ever produced or could ever produce. The Moon has been struck. The dust on the Moon has been struck. The Sun is being struck continuously, in such numbers that the surface is, in a literal sense, a slow-motion fireworks display of cosmic ray-induced particle showers, invisible from Earth but real. The neutron stars in the catalogue, every one of them, are being struck. If the lawsuit's worst fear were possible, none of those objects would still be there. The sky would not look the way it looks. The argument that closed the case in Honolulu was not made by a courtroom. It was made by the persistence of every star you can see overhead. The universe is a much larger laboratory than the one underneath Geneva, and it has been running this experiment for 4 billion years, and the answer it has given is that nothing happens. The argument goes further than the casual statement Kutu made, because some skeptic somewhere will always say, well, maybe the cosmic ray collisions are slightly different from the LHC's collisions in some way that matters. Maybe the geometry of a cosmic ray striking a stationary nucleus in the upper atmosphere is different from the geometry of 2 protons meeting head-on inside a collider. Maybe the products of such collisions, if they were dangerous, would not be confined the way the lawsuit feared they would be. To address even that possibility, 2 physicists named Stephen Giddings and Michelangelo Mangano published in 2008 a paper called Astrophysical Implications of Hypothetical Stable TV-Scale Black Holes. The paper appeared in Physical Review D. It was in essence an attempt to close even the most paranoid remaining loophole. Giddings and Mangano asked the following question. Suppose, against all the arguments that Hawking radiation would evaporate the black hole almost instantly, the black hole was stable. Suppose it was neutral, so it did not lose energy to interactions with charged matter. Suppose it persisted. Suppose Hawking radiation, for whatever reason, failed. What would happen to it? Their calculations showed that even in that worst-case scenario, the time required for such an object to accrete enough matter to pose any threat to Earth exceeded the age of the universe. The object would be too small, too gravitationally weak, too slow to find more matter to grow on. It would, in any reasonable timeline, do nothing. And more damning still, Giddings and Mangano pointed out, dense stars like white dwarfs and neutron stars, bombarded by cosmic rays for billions of years, would have already destroyed themselves if the scenario had any truth to it. White dwarfs have densities of about 1,000,000 grams per cubic centimetre. They have been cosmic ray targets for as long as they have existed. If even one such hypothetical stable micro-black hole had ever formed in the atmosphere of a white dwarf, in all the white dwarfs in the visible universe it should, in the time available, have eaten the white dwarf. White dwarfs would be unstable. The catalogues of stellar remnants would not look the way they look. The catalogues do look the way they look. White dwarfs are still there. Neutron stars are still there. The argument in retrospect was decisive before the LHC ever switched on. The lawsuit in Hawaii was not dismissed because the science was hidden. It was not dismissed because the judge was deferring to authority. It was dismissed because the universe had already run the experiment the plaintiffs feared. It had run it on every star, every moon, every rock in the solar system, every neutron star in the galaxy, every white dwarf in the catalogue, every night for the 4 billion years the Earth has existed and the much longer history of the cosmos beyond it. The answer kept coming back the same. Nothing happened. The lawsuit was, in a way, asking a question that had already been answered by the persistence of objects in the sky. It just had not noticed. The cosmic ray argument has another consequence that is worth thinking about, because it tells you something about how science answers the kind of question the lawsuit was asking. The cosmic ray sky is not a single experiment. It is a continuous experiment, run by nature, across all of space and time, with statistics that no laboratory could ever match. If you want to know whether a process at energies inaccessible to your laboratory is dangerous, you do not have to wait for your laboratory to reach those energies. You can look at the sky and see whether the process has already been observed at higher energies elsewhere. The sky is the most patient, most thorough, most statistically powerful collaborator any experiment could ever have. The Large Hadron Collider, in 2008, when the lawsuit was filed, was about to do something that nature had been doing in the sky for 4 billion years already, only at energies far higher. The sky had not produced any disasters. It was a reasonable expectation that the collider would not either. The reasonable expectation in this case was simply correct. Part 8. The first time. Humans looked for a black hole, they made themselves. In October of 2010, only months after the Large Hadron Collider had begun producing collisions at high energies, the CMS collaboration ran the first dedicated search for a microscopic black hole in human history. The fact of the search, and the date of the search, deserve a moment of attention before the result. The lawsuit had been filed in 2008. The collider had circulated its first beams in September of 2008, only to suffer a magnet incident a week later that delayed the start of physics operations until the autumn of 2009. By 2010, the machine was running at 7 TeV of collision energy, half of its eventual design. CMS had been accumulating data. The collaboration had decided, as one of the first physics searches it would undertake, to look for the signature Dimopoulos and Landsberg had described. The search was, in a real and literal sense, the lawsuit being answered. 2 years after a federal courtroom on Oahu had heard the case for stopping the collider before it could produce black holes, the collider had run and the collaboration had looked. The signature the search was designed to detect was specific, and it was guided by the theoretical predictions. A microscopic black hole, if it formed in the way ADD predicted, would decay into many particles at once. Hawking radiation, applied to a TeV-scale black hole, predicts a thermal spectrum of every standard model particle type, emitted in roughly equal proportions in all directions. The decay products would carry a total transverse energy far above anything an ordinary collision would produce. They would emerge from a single point with a quasi-spherical distribution, not the collimated jets that come from ordinary Proton scattering. The pattern would be too busy and too symmetrical to come from the standard interactions of quarks and gluons. The standard model, when you simulate it on a computer, simply does not produce events that look like that very often. A real black hole event, if one happened, would be the most distinctive thing in the data. CMS filtered the collisions they had collected for that shape. They had 35 inverse picobarns of data at 7 TeV. By modern standards, this is a small dataset, a tiny early-run sample, the kind of thing you take to calibrate your detector and learn to do your job. But it was enough to ask the question. The search algorithm looked in particular at events with 8 or more high-energy objects in the final state, where the total transverse momentum of the objects exceeded various thresholds. It compared the count of such events in the data against the number predicted by the standard model. The result was clean. Every event the search algorithm flagged was explained by the standard model. There were no anomalies. There were no candidates. There was no excess. The number of events at high multiplicity was, within the statistical uncertainties, exactly what the standard model predicted. Whatever was producing the LHC's collision events, it was not producing microscopic black holes at the rate that ADD had implied. The result was written up by the CMS collaboration and submitted to the journal Physics Letters B, where it was published in 2011 under the title Search for Microscopic Black Hole Signatures at the Large Hadron Collider. It was the first direct experimental limit on micro-black hole production ever set. Microscopic black holes, the paper concluded, were excluded for masses between approximately 3.5 and 4.5 TeV across a range of ADD parameters. The range expanded as the data accumulated. The lower bound on the fundamental gravity scale, in the simplest ADD scenarios, was pushed higher. The phrase that earlier in this story we identified as the kernel of the prediction, space-time cannot decline, returns here with a quiet inversion. In the simplest ADD universe, space-time would have had to do this thing. 2 partons inside a proton-proton collision, passing close enough, would have had to fold themselves into a horizon. Once the geometry was met, the formation was inevitable. That was the prediction. The result of the first dedicated search, and of every search that has followed in the years since, is that whatever else space-time might be doing inside the Large Hadron Collider, it is in fact declining to do this. Either the simplest ADD picture was wrong about the relationship between the LHC's energies and the higher dimensional Schwarzschild radius, or the entire framework was wrong, or some other ingredient, some quantum gravity uncertainty correction, some additional condition on horizon formation, was preventing the geometry from being met in the way the theory had said it would be. The space-time in the LHC's beam pipe, faced with the conditions that ADD said would force it to make a black hole, has, in case after case after case, declined. The searches did not stop with the first paper. The CMS analysis was repeated with more data, at higher energies, with more refined techniques. The Atlas collaboration ran its own independent search with different cuts, different triggers, different statistical methods, and found the same thing: no candidates. Through Run 2, from 2015 to 2018, the collider ran at 13 TeV. Atlas and CMS each accumulated something like 140 inverse femtobarns of proton-proton data. The searches were updated. The lower bound on the fundamental gravity scale in ADD scenarios was pushed past 9 TeV, then 10 TeV, then beyond. Different versions of the model, with different numbers of extra dimensions, were ruled out one after another. The remaining parameter window narrowed. Run 3 began in 2022, at the slightly higher energy of 13.6 TeV. Atlas, alone, collected roughly 165 inverse femtobarns of proton-proton data in the first 3 years of Run 3. That number, on its own, is more than the entire Run 2 integrated total. The signature the physicists were looking for has not appeared, not in the original simple form, not in any of the more sophisticated variants that theorists have proposed in the intervening years. The democratic, high-multiplicity, quasi-spherical bursts of particles that would mark the death of a microscopic black hole have, across 2 decades of running and across 4 detectors, and across hundreds of inverse femtobarns of accumulated data, simply not been observed. A theory that predicted a specific striking event that told experimenters exactly where and how to look for it, and an experiment that looked carefully and saw none. That is not a draw. That is the universe telling you something. Every year that the LHC runs without producing the signature, the window of possibility for ADD in its simplest form gets smaller. The fundamental scale of gravity, if it sits where ADD said it sits, and only there, has been pushed past the energy reach of the current machine. The remaining parameter space is, by the standards of theoretical physics, narrow. The simplest, most beautiful version of the picture that 1998 had proposed is, by the increasingly compressed margin of what the LHC has not seen, effectively ruled out. The Hawaii lawsuit was, in the most literal possible sense, answered by these searches. The lawsuit feared the production of black holes that would consume the Earth. The Collider has searched exhaustively for the production of black holes of any kind that could conceivably have come from the theory the lawsuit was leaning on, and the production rate is, within the statistical precision of one of the most thorough searches ever conducted, 0. There are no black holes, there is no production, the signature is absent. If the answer feels anticlimactic, that is appropriate. Most of physics is anticlimactic, in the way that most science is anticlimactic. A question is asked, a measurement is made. The measurement returns a number. The number is interpreted. The interpretation either supports or refutes a hypothesis. Sometimes the interpretation produces a Nobel Prize. Sometimes the interpretation produces a footnote in a long paper. The CMS search for microscopic black holes in 2010 produced a footnote. The footnote said, in effect, this thing some people were afraid of cannot be happening because we looked and it isn't. The lawsuit, by the time the footnote was written, had been dismissed for 2 years. Walter Wagner had stopped giving television interviews. The Collider was running. The first hints of the Higgs boson were beginning to appear in the data. And in a quiet corner of the CMS analysis pipeline, a search algorithm was filtering events for the signature of a horizon that, as far as anybody could tell, the universe had declined to make. The absence of a result in physics is often the most informative result. A signal is one thing. An absence, when you have looked carefully enough and long enough, and at high enough sensitivity, is another. The absence of microscopic black holes at the LHC is, in the way that physics learns from absences, the universe's way of telling us that ADD in its simplest form is not how the universe is built. The hierarchy problem remains. The 17 orders of magnitude between the weak scale and the Planck scale remain. The Higgs is still suspiciously light. Whatever protects it, whatever solves the problem the ADD authors were trying to solve, it is not the geometric leak they proposed. The answer is somewhere else. We do not yet know where. Part 9. The desert that should not be empty. The 17 orders of magnitude between the weak scale and the Planck scale have a name. Physicists call it the desert. It is one of those words physicists use that, the more time you spend with it, the heavier it gets. The desert is the range of energies between roughly 100 giga-electron-volts, where the W and Z bosons and the Higgs live, and roughly 10 to the 19th giga-electron-volts, where gravity, in the standard picture, becomes important. The desert spans 17 powers of 10. Decades of experimental work at accelerators all over the world have probed the lower end of it. The LRP Collider at CERN searched up to about 200 GeV. The Tevatron at Fermilab pushed past 2 TeV. The LHC in Run 3 is probing up to about 13.6 TeV at the collision level, and to several TeV in any individual analysis. In all of those experiments, in all of those analyses, in all of the runs and integrated luminosities and trigger menus, almost nothing new has been found. The Higgs boson, of course, has been found. The Higgs is the great exception. The Higgs sits at 125 GeV, and its discovery in 2012 completed the particle content of the Standard Model. The Standard Model in its current form has now been experimentally confirmed in every particle and every coupling it predicts. There is no missing particle in the Standard Model. There is no missing interaction. The model in the energy range we have explored is empirically complete. The completeness is, in some sense, a triumph. It is the culmination of a half-century of theoretical and experimental work. It is one of the most precise scientific theories in human history. Its predictions match experimental measurements, in many cases, to 10 or more decimal places. The Standard Model works. There is no doubt about that. But the Standard Model is not the same thing as a complete theory of nature. It does not include gravity. It does not include dark matter, which we know from astronomical observations exists and constitutes about 5 times the mass of ordinary matter in the universe. It does not include dark energy, which is responsible for the accelerated expansion of the universe and constitutes most of its total energy density. It does not explain why the Higgs has the mass it does. It does not explain why there are 3 generations of fermions. It does not explain the patterns of fermion masses, which span 12 orders of magnitude from the electron to the top quark. The Standard Model is empirically successful within its domain, but its domain is small compared to the question of what nature actually is. There is, in all of these respects, room for new physics. There has to be. The Standard Model alone does not and cannot be the whole story. The puzzle is that, within the range of energies the LHC can probe, the new physics that would solve any of these problems has so far not appeared. The simplest extensions of the Standard Model, supersymmetry and many of its variants, with the partners at masses just above the Higgs, extra dimensions in the simplest ADD form, with the fundamental Planck scale at the TV level, composite Higgs models that build the Higgs from a deeper layer of strongly interacting physics at a few TV, new heavy-gauge bosons of various kinds, have all been searched for, in many cases extensively, in many cases for years. None of them has produced a confirmed discovery. The lower bounds on the relevant masses have been pushed higher and higher. The natural windows have been closed one after another. The desert, the long stretch between the weak scale and the Planck scale, remains, in our explorations of it so far, empty. The emptiness of the desert is its own anomaly. It is not, for most people, the kind of anomaly that pulls at the imagination. There is no specific monster in the desert that physics is failing to find. There is instead the absence of any monsters at all, across a range of energies that, if the principle of naturalness has any teeth, should have been thick with them. The most beautiful versions of the most beautiful theories have predicted new particles in the desert, and those particles have not been found. The simplest natural solutions to the hierarchy problem have predicted measurable consequences, and those consequences have not appeared. The Higgs, sitting alone at 125 GeV, looks lonelier the further out the bounds on its companions are pushed. The 17 orders of magnitude between the weak scale and the Planck scale stretch ahead of us, increasingly featureless. The strangeness of the universe is not that some particular thing is broken. The strangeness is that the universe is built in a way that, on the deepest principles physicists have come up with so far, ought to look very different from how it looks. The universe is, in this specific way, not natural. It is, in this specific way, fine-tuned. And we do not yet know what the fine-tuning means, or how to escape from it, or whether there is something we have profoundly misunderstood about what we should expect from a fundamental theory in the first place. One way the absence in the desert has affected physics is methodological. The principle of naturalness, for decades, was treated almost as an axiom in particle physics. Theories were judged by how natural they were. Models were preferred that solved the hierarchy problem with the lightest particles, because lighter particles meant more natural solutions. Experimental searches were prioritized for the most natural regions of parameter space first. The expectation, into the early 2000s, was that the LHC would turn on and the desert would, in some way, be populated. The first 100 inverse femtobars of LHC data would be the moment of revelation. The new physics would arrive, naturalness would be vindicated, and the next chapter of fundamental physics would begin. The first 100 inverse femtobars of LHC data came and went. The new physics did not arrive. Naturalness was not vindicated. Some physicists have responded by maintaining that the new physics is there, just at slightly higher scales than the most natural versions of the theories predicted. There may yet be supersymmetry at 5 or 10 TeV. There may yet be extra dimensions with a fundamental scale slightly above what the current bounds rule out. The desert may have its monsters. They may simply be hiding a little higher than expected. Other physicists have responded more radically. Maybe naturalness is not the right principle. Maybe the universe is fine-tuned, and the explanation, if there is one, is not in a hidden symmetry or a deeper structure, but in something like the anthropic principle. The idea that the parameters of physics are what they are because they are the parameters that allow observers like us to exist, selected from a vast ensemble of possible universes by the simple condition of being inhabitable. The anthropic explanation has a long history. It has its defenders and its critics. Some physicists find it deeply uncomfortable, because it pushes the explanatory power of physics away from first principles and into the conditions of our existence. Others find it the only honest response to a universe whose parameters increasingly look not derivable from a deeper principle, but selected from a landscape of possibilities. The most influential proposal that combines anthropic reasoning with a deeper theoretical framework is what has come to be called the string landscape, an enormous number of possible solutions of string theory, each one corresponding to a different effective theory at low energies, each one with different particle masses and different couplings, and only some of them allowing the kind of stable, structured, life-supporting universe we observe. Whichever way the field goes, the empty desert has changed the conversation. ADD in particular was the kind of proposal that was supposed to make the desert disappear. ADD said the desert is not there. The desert is an illusion produced by mistaking the four-dimensional Planck scale for the fundamental scale. The fundamental scale in ADD is right at the edge of the weak scale, and the desert is folded up into the extra dimensions, where it is hiding in plain sight. If ADD had been right, the absence of physics in the desert would have been not an embarrassment but a confirmation. The desert would not have been a puzzle. It would have been a misreading of the geometry. ADD was not right. The LHC has, by its absence of results, told us this. The desert is real. The 17 orders of magnitude really are there. The reason the Higgs is light, the reason gravity is weak, the reason a paperclip jumps to a fridge magnet against the entire pull of the planet has nothing to do with the simplest version of large extra dimensions. The explanation, whatever it is, must be something else, something we have not yet thought of in a form sharp enough to test, or something we have thought of but cannot test with the machines we have. The future of the question is what we will look at next. The Large Hadron Collider, for all its remarkable accomplishments, is not the last word. It is, in the longer story of accelerator physics, an early chapter. The plans for the next chapter are already on the drawing board. The next chapter will, with high probability, settle whether the desert remains empty into a far greater range, or whether the structure we have been searching for has just been hiding a little farther out than we could currently reach. Either answer would be one of the most significant results in the history of fundamental physics, and either answer is coming in some form within the lifetime of most people listening tonight. Part 10. Closing the door from a different direction. The most recent chapter in this story is in some ways the strangest of them all, because it is the chapter in which theorists, looking back at their own work from 25 years earlier, have begun to argue that the original picture, even in its most generous reading, may not have made the prediction that turned out to fail. The argument is technical, but the substance can be stated cleanly. In 2023, a group of physicists led by Matthew Lake published a paper in the journal Frontiers in Astronomy and Space Sciences. The title was modest and the content was not. The paper argued that even if extra dimensions are real, the rules of quantum uncertainty in higher dimensional spacetimes may prevent microscopic black holes from forming at LHC energies at all. To understand why this argument is interesting, you have to take seriously the fact that black hole formation, in the ADD picture, involves spacetime at scales where the classical concept of a Schwarzschild radius is no longer obviously well defined. The Schwarzschild radius is a feature of classical general relativity. It is the radius at which, if you treat spacetime as a smooth, continuous manifold, an event horizon forms around a given concentration of mass energy. But at distances close to the Planck length, spacetime is not smooth. It is, in any reasonable expectation of how a quantum theory of gravity would behave, fluctuating, foamy, ill-defined in a way that classical geometry does not capture. The Schwarzschild radius in the ADD picture, around an automata, is small enough that quantum corrections to the geometry may be significant. They may not just be a small correction, they may dominate. Imagine yourself standing at the threshold of a small room. The walls have been arranged for a door, the hinges are in place, the frame is built, there is a clear plan for what the door is supposed to look like, what it is supposed to do, how it is supposed to open. But when you try to fit the door into the frame, it does not quite fit. The dimensions are off, slightly. The door is the right shape on paper, the room is the right shape on paper, but in the actual three-dimensional reality of the room, with the walls slightly bowed and the frame slightly warped and the floor slightly tilted, the door cannot find its way into the gap that was supposed to receive it. You stand and look at the threshold. Everything you can see is the same as it was in the plans, but somehow, when you take the plans into the world refuses to do what the plans said. That is the kind of refinement Lake and his colleagues are pointing at. The geometry of the ADD black hole, sketched on a chalkboard, was clean. The geometry of the ADD black hole, lifted off the chalkboard and into the strange quantum-corrected fabric of space-time at atometer scales, may not quite be able to settle into the shape that the calculations said it should. The technical apparatus the paper deploys is called the generalized uncertainty principle. It is a modification of the ordinary quantum mechanical uncertainty principle that includes corrections from quantum gravity. Ordinary uncertainty says that you cannot know both the position and the momentum of a particle to better than a certain product, set by Planck's constant. The generalized uncertainty principle says that when gravity is involved, there is an additional contribution. At very high momenta, the position uncertainty does not just stop decreasing, it increases because the energy concentrated in trying to localize the particle warps the geometry. There is a minimum length scale below which the concept of localization stops making sense. For Planck scale phenomena, the minimum length is of order the Planck length. For ADD-style phenomena at the TeV scale, the minimum length in higher dimensions is correspondingly larger. Lake and his colleagues calculated the consequences of this generalized uncertainty principle for the formation of microscopic black holes in the ADD framework. Their result was that the corrections pushed the formation threshold higher than the LHC's center of mass energies. Even if extra dimensions exist with a fundamental scale at TeVirus, the geometric conditions for horizon formation, when you account properly for quantum gravity, cannot be met by partons inside protons at 13.6 TeV. The door, in the metaphor we just used, does not quite fit. The room may exist, the walls may be in the right place, but the act of fitting a horizon into the geometry, at the scale required by the energies the LHC produces, may simply be forbidden by the rules of the underlying quantum theory. If Lake and his colleagues are correct, the absence of microscopic black holes at the LHC is not, by itself, a falsification of ADD. It is instead a confirmation of a different set of assumptions about what quantum gravity does at small scales. The door the original ADD theory opened may never, in any version of the universe, have been an open door. It may have been a door that, on closer inspection, was held shut by exactly the corrections that the chalkboard derivation neglected. This is the kind of conclusion that physicists hold loosely. It depends on a particular form of the generalized uncertainty principle, which is itself a guess about how quantum gravity behaves. Different versions of the principle, or different theoretical frameworks, may give different answers. But the broader point, that the absence of LHC black holes may be more informative than even the original theorists had imagined, is one of the strange and unexpected developments of the last few years. There is a sense, looking at this story from a distance, in which the lawsuit and the experimental program and the theoretical refinement have all been part of a single long conversation. The lawsuit asked, in its frightened way, whether something dangerous might happen. The experimental program asked, in its careful way, whether something predicted by a particular theory would happen, and the theoretical refinement is now asking, in its mathematical way, whether the prediction was ever quite as cleanly entailed by the theory as the original calculation suggested. All three of these threads have, in the end, given the same answer about the immediate question. The Large Hadron Collider has not produced microscopic black holes, the world has not ended, and the framework that would have made the production possible was, on closer inspection, perhaps less likely to make that prediction than the chalkboard version implied. The closure of the question in retrospect has come from several directions at once. Part 11. Where the question goes next. The Large Hadron Collider is not the end of the story. It is, in the longer story of accelerator physics, more like a middle chapter than a conclusion. The current machine has, by 2026, accumulated an enormous body of data and explored the energy frontier as it currently exists. It has discovered the Higgs. It has constrained more sharply than any prior experiment the space of possible new physics. It has answered, by what it has not found, a particular form of the question the lawsuit was asking. But there are at least 2 more chapters being written, both of which will sharpen the answer and possibly reopen the question in forms the LHC was never built to address. The first of those chapters is the high luminosity LHC. The plan is to upgrade the existing collider during a long shutdown beginning around 2028 and resuming physics operations around 2030. The upgrade will not push the collision energy significantly higher. The LHC's energy is set by its size and its magnet technology, and the magnets are already operating near the limits of what current superconducting technology can deliver. What the upgrade will do is increase the luminosity, the rate of collisions per second, by roughly a factor of 5 to 10. Over the lifetime of the high luminosity program, the integrated dataset will grow from the few hundred inverse femtobarns of the current machine to roughly 3,000 inverse femtobarns. 10 times the data, at essentially the same collision energy. 10 times the data is not nothing. It will not solve the hierarchy problem on its own. It will not reopen the simplest ADD picture if the simplest ADD picture has truly been ruled out at lower luminosities, but it will, with another decimal place of statistical sensitivity, allow searches for rarer processes than the current data can reach. New regions of parameter space in many extensions of the standard model will be probed. The most precise measurements of the Higgs boson's couplings to other particles will be made. If there is any small deviation from the standard model in the Higgs sector, any hint that the Higgs is not exactly what the standard model says it is, the high luminosity LHC has the best chance of finding it. The program will run, in its current planning, through the late 2030s, possibly into the 2040s. It is the immediate future of accelerator physics, and it is already, in concept, well underway. The second chapter, more speculative but more dramatic, is the Future Circular Collider. The Future Circular Collider, or FCC, is a proposed machine that would sit at CERN in a new tunnel, with a circumference of roughly 90 kilometers. The current LHC tunnel is 27 kilometers. The FCC would be more than 3 times larger. The geological surveys for such a tunnel are already underway. The civil engineering studies have been completed in initial form. The political and financial commitments have not been finalized, but the conceptual work is mature. The proposed program for the FCC is, in 2 stages, an electron-positron precision machine first, and then a proton-proton energy frontier machine second. The proton-proton stage, called FCCHH, would operate at a collision energy of 100 TeV, 7 times the energy of the LHC. At 100 TeV, a great many of the questions the LHC has not been able to answer come within reach. A 2024 analysis by Halil Gul and his colleagues estimated that a 100 TeV collider could probe fundamental gravity scales up to roughly 45 TeV. That is a sensitivity that would, in essentially every reasonable version of ADD and its cousins, decisively close or confirm the remaining parameter window. If extra dimensions exist with a fundamental scale anywhere below about 45 TeV, the FCCSH will find them in some form. If the FCCSH sees nothing at the gravitational sector, the simplest extra-dimensional escape route from the hierarchy problem will be effectively closed forever. The desert will, at that point, be confirmed empty, all the way out to scales that no theoretical proposal can call natural with a straight face. The hierarchy problem will, at that point, become one of the most acute embarrassments in modern theoretical physics. The burden of explanation will pass to ideas more radical than ADD ever was, perhaps to the anthropic landscape of string theory, perhaps to something nobody has yet written down. The phrase that recurs through this story has, I think, the right weight to return one more time. A paperclip jumps to a magnet against the entire pull of the planet. The image, which earlier in the script seemed almost charming, lands with a different weight now. We have been on a long tour. We have watched the most beautiful theoretical proposal of the last 30 years rise and by every indication fall. We have watched the world's most ambitious experiment run for 15 years without producing the consequences that proposal predicted. We have watched the door that the proposal seemed to open turn out, on closer inspection, to be a door that perhaps was never fully open. And at the end of all of it, the paperclip is still jumping. The 17 orders of magnitude are still there. The Higgs is still suspiciously light. The kitchen table experiment that summarizes the deepest unsolved problem in physics is unchanged. The first time you heard it described in this script, it was a curiosity. By now, it is a problem with a long history of failed solutions, and it remains as unresolved as it was on the day the ADD paper was written. The future of the question is not just bigger machines. There are theoretical programs that propose to attack the hierarchy problem from completely different angles than ADD ever did. Composite Higgs models, whether Higgs is not an elementary particle, but a bound state of more fundamental constituents at a scale a few times higher than the LHC has explored. The relaxation idea, whether Higgs mass is the result of a dynamical relaxation process in the early universe, slowly settling to its observed value as cosmological evolution proceeded. The naturalness proposal, in which the apparent fine-tuning of the Higgs is explained by the existence of an enormous number of copies of the standard model, all with different Higgs masses, only some of which happen to allow observers. None of these proposals are obviously correct. None of them is obviously wrong. All of them are alive, in the technical sense, and all of them are waiting for experimental input. That input will, in part, come from the next generation of accelerators. It will also come from theoretical work that nobody has done yet, and that, by definition, cannot be planned for. The Honolulu lawsuit, in its strange way, was a precursor to all of this. The lawsuit was asking, in its frightened, badly articulated way, whether the universe was about to reveal itself to be something other than what the standard textbook picture said it was. The answer the universe has given in 15 years of LHC operation is partial. The simplest version of one specific alternative, extra dimensions with the geometry the ADD authors proposed, has been, by an increasingly tight margin, ruled out. The universe is not that. But what the universe actually is, the structure of reality that underlies the 17 orders of magnitude and the light Higgs and the apparently weak gravity, remains as open a question as it has ever been. The door, in this respect, has not closed. The door has widened onto a longer hallway. The lawsuit will turn out, looking back, to have been the rough draft of a question that physics is, in the present moment, still inside. Part 12. The lawsuit was afraid of the wrong thing. The Hawaii lawsuit was afraid of the wrong thing. The Large Hadron Collider was never going to swallow the Earth. The cosmic ray sky and Hawking's calculation had already settled that before the first beam circulated. The first dedicated search at CMS confirmed it. Run 2 confirmed it. Run 3 has continued to confirm it. Every year that the collider has operated has been another year in which the lawsuit's specific fear has been disproved by simple absence. There are no Earth-eating black holes inside the apparatus. There never were. The lawsuit's worst-case scenario was always, in the most quantitative sense available to physics, a thing the universe had decided would not happen. Underneath the fear, though, was a serious question. The serious question was not whether the collider would destroy the world. The serious question was whether the universe is stranger than it looks, whether the 3 dimensions we can see and the 4 forces we can measure are all there is, whether the gentle gravity that lets a paperclip jump to a fridge magnet, with the entire mass of the Earth losing the contest, is the whole story of gravity, or just a fraction of it. The ADD framework was one specific falsifiable answer to that question. Gravity seems weak because it leaks somewhere else, the framework said, and a powerful enough machine could catch a piece of the leak. Physicists built the machine. The leak has not shown up. That absence is its own result. The Hawaii lawsuit was, in a way, a primitive version of the question physics was already asking itself. The lawsuit was reading a real moment in the history of the field, even if it was reading it through the wrong lens. Wagner and Sancho thought they were trying to prevent the end of the world. What they were actually doing, without knowing it, was demanding that physics finish answering a question it had not yet finished asking. And physics, in the years since, has been doing exactly that. The universe has given a partial answer. The simplest version of one specific alternative to the standard picture has been, by an increasingly tight margin, falsified. Whatever ultimately replaces it will, with high probability, be more complex than what Arkani Hamed, Dimopoulos and Diwali proposed in 1998. This is how physics is supposed to work. A theory makes a prediction. The prediction either appears in the data, or it does not. The interpretation either supports or refutes the theory. The space of possibilities narrows. Over time, generation by generation, paper by paper, the picture gets sharper. Not because anybody planned it, but because the experiments and the calculations and the searches and the careful, slow, patient work of thousands of people across decades cumulatively forced the picture to converge on something closer to what nature actually is. ADD made a clear prediction. The prediction failed. Physics learned something. The field moves on. Gravity is still pathetically weak. A paperclip still jumps to a fridge magnet against the pull of an entire planet. The 17 orders of magnitude in the desert are still there, still silent, still waiting. The extra dimensions could exist at scales smaller than anything we can currently reach. They could be absent entirely. The hierarchy problem could turn out, in some way nobody has yet articulated, not to be a problem at all, but a clue pointing somewhere nobody has thought to look. The most honest sentence in modern physics remains what it has always been. We do not know yet. Beneath the border between France and Switzerland, the collider is still running. The 2025 Proton run finished in early December with record performance. The high luminosity upgrade begins at the end of this decade. A much larger machine, the Future Circular Collider, sits on the drawing board with its first geological surveys already underway. Each new machine will ask a sharper version of the same question that the 2008 lawsuit was stumbling toward. Somewhere in the data that these machines will eventually produce, or in theories that nobody has written yet, the next piece of the answer is hiding. It is a strange thing to fall asleep inside an unanswered question. It is a stranger thing to realize that all of physics, in the present moment, is doing exactly that. The Honolulu lawsuit asked a frightened version of a real question, and the frightened version has been answered, and the real question is more open than it has ever been. The universe has not finished telling us what it is. The kitchen table experiment with the paperclip is still the deepest puzzle in physics. The walls of the desert have not yet shown a door. The fundamental scale of gravity has not yet announced itself. The next chapter of the story is being written, every day, in the underground tunnels of CERN and on the chalkboards of theorists, and in the data archives of detectors collecting events at a rate of 40 million per second. Being inside that question, listening to the sound of physics still working on it, is a kind of privilege. It is the privilege of living at a time when the deepest things have not yet been settled. The lawsuit, for all its strangeness, was a clumsy and human version of that same privilege. Wagner and Sancho thought they were trying to stop the world from ending. They were, without knowing it, taking part in the longest-running conversation our species has ever had with the universe. The conversation has continued without them. The next thing the universe says will, when it arrives, change the shape of what we know. Until then, the paperclip jumps, the 17 orders of magnitude wait, and the collider, in its tunnel beneath the border, continues, patiently, calmly, to ask.